Okay, good morning. How many of you watched the video? I don't know how many did, but because I can only see the number of views. Well, I hope some students did at least. Otherwise, today's lecture is not going to make much sense. AC power. AC power is a guaranteed problem in the final exam. All right, so let's take a look. There we go. All right, so power in AC circuits. What it is, why it's important. I'll just do a brief recap. So resistive circuit analysis, when you apply DC or when you apply AC, resistors behave exactly the same way, right? Energy is transferred, resistors absorb the energy and dissipate the excess energy as heat. Inductors and capacitors, however, are energy storage devices, and because they store energy, if you apply a AC alternating waveform to an inductor or capacitor, the energy will flow in one half cycle and it will flow out in the other half cycle, right? So it's constantly flowing in and out, in and out. There is, of course, also reactance associated with the capacitor and the inductor. And so the power that is associated with the inductor and capacitor has to do with the reactance, and hence the name of that power, reactive power. So for a resistor, we term the power as real or average power because that power is doing the actual real work of converting the electrical energy into useful mechanical energy. The reactive power does not do any real work except it sets up the magnetic fields and the electric fields, sets up the the power associated with the reactance. So reactive power is not really consumed. Okay, it's not really consumed. It's simply flowing in and out of the inductor and the capacitor. So if you have a utility company that is hundreds of miles away from a customer, you have transmission lines running hundreds of miles, the utility company is not only sending real power, it is also has to send reactive power. The reactive power will be absorbed by the inductive load and it will be sent back. Constantly traveling back and forth along the lines is going to cause a huge power loss, right? So the reactive power, again, even though it's not doing any real work, is traveling back and forth across the transmission lines. When you send electrical power over long distance transmission lines, power loss occurs. We wanted to keep that power loss as small as possible. Okay, and that's basically what you're going to study here. How to analyze a circuit, how to find the power associated with the resistor, inductor, and capacitor, and also find the total power associated with the source or associated in the circuit. So mathematically, because reactance is represented with the imaginary number, we use the same convention and we represent reactive power also with the imaginary number. Total power would be the real power plus the reactive power. So it's real power plus the reactive power. Because P is real and Q is imaginary, we say that the total power is total complex power. It's noted by S. Real power or average power still has a notation of P. Reactive power has a notation of Q. A resistor does not have reactance, so resistor only has P. Capacitors and inductors do not have any resistance, so they only have Q. So we have QL and QC for inductors and capacitors. Units for all three are different. Units for real power or P is watts. Reactive power is volt ampere reactive, VAR, and total complex power is VA, volt amperes. These are some of the equations that we use. We have the power triangle, similar to the impedance triangle. Real power P is on the real axis. Imaginary reactive power Q is on the imaginary axis. Now, again, this is just a mathematical representation. Reactive power, when we say is represented by the imaginary number, does not mean that the reactive power is imaginary. It's a mathematical representation. Okay, has a physical basis in real life. So reactive power has a physical basis, right? It's not imaginary. It's not a construct of the mind. It's just mathematical representation with the imaginary number. All of the previous equations that we learned still apply. So P is equal to I squared times R. P is also equal to V squared over R. So we talk about the inductor and the capacitor, which has reactance. Reactance is X, right? XL is omega L. XC is 1 over omega C. So the same equations still apply. For a component, actually, let's go back here. Said we can find P and Q using these equations, right? We can find P and Q using these equations. You have to keep in mind, if you want to find P for a component, you need to find the voltage and current for that component, as well as the power angle for that component. The power angle for any specific component is the phase difference between the voltage minus the current. So theta V minus theta I, that gives us the power angle. Again, it's the same as the impedance angle. Impedance Z is V divided by I. When you divide two complex numbers, the phase angles get subtracted. So theta V minus theta I. So power angle theta is the same as the impedance angle theta, no different. Excuse me. So again, when you want to find P and Q for a particular component, you need the voltage, the current, and the power angle for that specific component. And the reason I'm harping on this is because we have the other equations also that work just as well, which is right here. I squared times R and V squared over R. These equations are preferable because the component value would already be known to us. We would already know what the resistor value is. We would already know what the inductor and the capacitor value is, meaning we can find XL and XL and XC, right? So if we already know the component values, why bother finding out two different quantities? We can find just the I for that component and do I squared times R or I squared times X. Or we can just find the voltage and we can do V squared over R or V squared over X. We don't need to find both I and V. Does that make sense? Right? These are all different tools. All of these equations are different tools in our toolbox. It is up to you to decide which equation you want to use. Yes. X is the reactance. Reactance is basically the opposition that a inductor and a capacitor has to changing of the input current or the input voltage.
What are the units for the current in AC? AAC or?
No, it's just amps. It's just amps. No, it's not. So it's the first A is amps, and then AC is just telling you it's reading AC. If you change it to DC, it's going to say ADC. Yeah. So if you're measuring voltage, next time you're in the lab, you can see it'll tell you VAC or VDC, and AAC or VAC. Okay. So let's get to our problem. We have a RLC circuit. We are applying a voltage. Yes. I asterisk is the, so total complex power S can be represented as, well, S, of course, in the previous equation, we saw S is equal to P plus JQ, rectangular coordinates. When you plot that on the complex plane, you get magnitude of S and you get the power angle theta. Alternative equation for total complex power S is half VI asterisk. The asterisk stands for the complex conjugate of that complex number. complex conjugate of a complex number is simply, you're basically simply changing the sign of the imaginary number. If it's a plus jb, it becomes a minus jb. So it stands for the complex conjugate. A plus jb simply becomes a minus jb. It's r with the phase angle theta. It becomes r with the phase angle minus theta. All right, let's get to our problem. So let's see. Okay, first things first. Well, the question asks us determine the power for every component. That's it, plain and simple. But it's a very loaded statement in the sense that we'd have to find a whole bunch of quantities first before we can even get to applying our equations, right? So what equations do we have? We have v squared over r, we have I squared times r, and then we have VRMS, IRMS times cos theta and sine theta, right? All of those equations, we need the voltage and or we need the current, V and I, right? So there are four components in here, RLC, and then the voltage source VS. This seems easy enough because if it's a voltage source VS, all we need to do is find the current and we can use half VI asterisk, or we can find P and Q and then add them up. Make sense? Hopefully. And then the components, we have L, R, and C. We find XL and XC, or ZL and ZC. And we can find the real power P for the resistor. We can find the reactive power Q for inductor and capacitor. In order to do that, we need the voltages and the currents. So before we can even begin applying the equations for power, we need to solve for the entire circuit. Find the voltages and currents in different parts of the circuit. So this would be an example of AC analysis from chapter 5. So I will go through the entire analysis step by step. We'll see how we can find the voltage and current, and then how we can apply the power equations. So first things first, draw the equivalent impedance diagram. Okay, draw the equivalent impedance diagram. And once we have this, we represent the voltage Vs with its phasor Vs. What can we say about R and ZC? Parallel, right? So we can combine them into one single impedance. And then how about ZL? It's in series, right? So R and ZC are in parallel, and that would be in series with ZL. We can combine everything together to form one single impedance, ZEQ. So here, I'm going to call this ZRC. ZRC is simply a combination of resistor in parallel with ZC. This is ZL. Total current I being supplied by the source is also the inductor current IL. IL is divided between the resistor and the capacitor. So IR and IC. This is V. And of course, ZEQ. Oh, sorry, VS. And ZEQ is equal to ZL plus ZRC and that's the total current I. Easy enough, makes sense, right? This is nothing new, right? Once you have the equivalent impedance diagram, you go back to chapter 2. Basically, how you can combine a resistive network, a large resistive network, reduce it down to one single resistance. That's the exact same technique that we apply here. The only difference is that the math is now with complex numbers, right? So that's the setup of the circuit diagram. Let's write the phasor for the voltage. Just 10, this becomes cos of 1000 T minus 90 degrees. And therefore Vs, the phasor for Vs has a magnitude of 10 and a phase angle of minus 90 degrees. Omega is 1000 radians per second. And ZL is J omega L. So J into 1000 into 0.1. Say J 100 ohms. It's also 100 with a phase angle of 90. ZC similarly is 1 over J omega C. Omega is 1000 into 10 microfarads. So all we are doing is just finding out the impedances in the complex quantities, ZL, ZC. Now you'll find ZRC. ZRC is the parallel combination of the resistor and the capacitor. ZRC can be written as, when you have two components in parallel, it's a product of the two divided by the sum of the two. So it is R times ZC divided by R plus ZC. So 100 into 100, 90. Oh, sorry, minus 90. And then R plus ZC should be 100 minus J 100. And again, as always, I would strongly recommend that you have your calculators out and you solve this as we go along for practice, just so that you get more and more comfortable solving these kind of problems. I got 10,000, 141.42 minus 45, 70.71 minus 45 ohms, and in polar rectangular coordinates, it's 50 minus J50 ohms. And then finally, ZEQ be ZL plus ZRC. ZL is J100. ZRC is 50 minus J50. So it's simply 50 plus J50 ohms. And in polar coordinates, I have the same magnitude, 70.71, with a phase angle of 45 degrees. All right. Take a few seconds, think over it. Let me know if you have any questions. Any questions at all? Right. So far, we have done is basically combine the entire circuit into one single impedance. So now I can apply Ohm's law and find the total current I that is flowing through the circuit. So by Ohm's law, find the total current I that is flowing through the circuit. I would simply be equal to Vs divided by Zeq. Point 1414 with a phase angle of minus 135. Now we can find the voltage across the resistor and the capacitor. They are in parallel, so obviously the voltage is the same. We can find that voltage by applying Ohm's law, right? I is the same current that is flowing through ZRC. So if I do I times ZRC, I would get VRC. VR is equal to VC, which should be equal to I times ZRC. Or to make things a little bit more fun, we can find the same voltage. Let's call it VRC. With voltage division, absolutely. So with voltage division, VRC would be a fraction of VS. Fraction would be given by ZRC divided by ZEQ. So 10 with an angle of minus 90. Is that my phone? Turn it on silent. I thought it was silent. Times ZRC, which is 70.71 with minus 45 divided by 70.71 plus 45. Final answer simply is 10, the angle of minus 180 volts. Magnitude of 10, phase angle of minus 180. Now, obviously, minus 180 is the same as plus 180. So if you do it on a calculator, you might obtain 10 with an angle of plus 180. Make sense, right? Whether you apply this equation or whether you apply this equation, your answer should be the same. I times ZRC, 0.1414 times what was ZRC? So 0.1414 times 70.71, that should give us 10 volts. Then you have minus 135 and minus 45, so minus 180. Okay, once we have this, let's find the current for the resistor, which would simply be VRC divided by R, and I get 0.1 with the angle of minus 180, and IC would be VRC divided by ZC, and I get 0.1, the angle of minus 90. So now I have the voltage across the inductor capacitor, the current for the inductor and capacitor. I have the current through the inductor. I can just apply it in the equations and calculate power directly. Note that we do not need to find IR and IC in order to find the power. We already have the voltage, right? If we have the voltage, I can simply apply the equation V square over R or V square over XC to find the power for the resistor and the capacitor. We do not need to find the current. I'm just finding it just to show you that we can use multiple equations to solve the same problem. Okay. So now we have the voltage, we have the current for every component. We actually don't have VL, but VL can be simply found by applying Ohm's law. VL would be I times ZL. I'll leave it up to you for practice. Okay, power equations. PR would be VR RMS square times R. And VR RMS would be magnitude of 10 from here divided by root 2. Oh yeah, divided by R. Thank you. Divided by R. Okay, so this would be 10 divided by root 2 square divided by R. 10 square 100 divided by 100. Cut off 1 over root 2 square, so half, meaning 0.5 watts. 0.5 watts. Alternatively, PR can also be found as IRMS square times R. Peak value is 0.1 divided by root 2 gives me RMS values square times 100. Again, gives me 0.5 watts. So IR peak value 0.1, RMS value is 0.1 divided by root 2. So IR RMS square times R 100. So it gives me 0.5. You do V square or R, you still get 0.5. So just a way of showing, doesn't matter which tool you use, your answer should be the same. Yes. No, this is, so that 0.14, where that one, 0.1414, that is the total current I. This is just the resistor current IR. Yeah. Where did it pop up earlier? Oh, you're talking about 70.71 ZEQ?
Yeah, that's how, yeah. I think he was saying
Oh, okay. Okay. All right. That's why I don't like leaving answers like that. Always like to have final values. Causes less confusion, at least to me. But did all of this make sense? Again, this is just the initial setup of the problem. You're just trying to find the voltage and currents. The actual work is beginning now. determine the power for every component. We just found the power for the first component. QL and QC. QL, again, we can have VL RMS square over XL. XL is simply omega L. We already found, which is 100. When you go out of class, find VL that I just assigned a student practice, plug it in here, find the value of QL. For now, in class, I'm going to solve it using this equation right here. ILRMS times XL. ILRMS would be 0.1414 divided by root 2, the whole square into 100. And I get 1 volt ampere reactive, 1 VAR. 1 VAR. QC is the same. Would be VCRMS square divided by XC. VCRMS would be 10 divided by root 2 into 1 over 100. Well, this is minus 100. The answer should be negative. And QC here, this comes out to be 0.5 VAR. Here it's ICRMS square times XC. Again, 0.14, oh, not 1414, sorry, 0.1 divided by root 2 square times minus 100 gives me minus 0.5 VAR. You put a negative sign because inductive power is always positive, capacitive reactive power is always negative. Real life, of course, power is never negative, energy is never negative. It is only for us to actually able to balance out equations. It also comes from the fact that the capacitor impedance would have a negative sign, right? The phase angle. Z is equal to V divided by I. So if Z is V divided by I, capacitor current is always plus 90 with respect to the voltage. So when you do V, theta V minus theta I, you always get minus 90. So it always has a negative sign. Inductive power is always positive. Capacitive power is always negative, pointing down. So if you add up PR and QL plus QC, total power in the circuit, P plus JQ, 0.5 watts plus J, 1 minus 0.5 gives you 0.5 plus J, 0.5, and this would be VA, volt ampere, total complex power in the circuit. And we can verify our answer because we still have one more component left, which is the source. The source, complex power, let's call it notation S. Okay, so total complex power S and a subscript of S for the source. So SS would be equal to PS plus JQS. Let's use the other equations this time. So VI cos theta, VI sin theta. P is VI cos theta or RMS values, obviously. And then Q, reactive power for the source, would be sin theta. Again, they are the three sides of a right angle triangle, right? P is the base, Q is the height, and apparent power magnitude of S is on the hypotenuse, the third side of the right angle triangle. That's where the sine and the cosine values come from. So PS would be, well, actually, let's find the power angle first. Power angle theta is the difference between the phase for the voltage and the current. Voltage has a phase of minus 90. The current has a phase of minus 135. So power angle theta is plus 45. So for the source is plus 45, which actually makes sense if you think about it. QL is 1 VAR, positive 1 VAR. QC is minus 0.5. So QL goes from 0 to 1. QC brings it down 0.5. Does that make sense? QC brings it down 0.5. So if you join this with 0, 0, it's still a positive angle. And it's positive 45. So P is VRMS times IRMS times cos of theta. VRMS for the source would be 10 divided by root 2. IRMS for the source would be 0.1414. 0.1414 divided by root 2 and cos 45. This comes out to be, surprise, surprise, 0.5 watts. Same thing with Q. And 0.5 VAR. So SS also turns out to be 0.5 plus J 0.5 VA. The exact same answer that we obtained earlier. No different. 0.5 plus J 0.5, 0.5 plus J 0.5. P is here on the X in the real axis, 0.5. Q, total Q is also positive 0.5, right? If QC was larger than QL, then total Q would be negative. Make sense? Right? If QC is always negative. So if QC was larger than QL, it would be negative. So power triangle for this would simply be, you have, actually, let's draw it down here. So if this is 0, 0, this is the real axis, P is right here, you got 0.5 watts. And you got 0.5 VAR. Both of them are the same length. This gives you magnitude of S. This is the power angle theta, which is 45. If you plot just the resistor and the inductor, you get PR 0.5. And then QL, let's do twice as much, right? So QL, which is 1 VAR, and from that same point, QC brings it down, which is 0.5. So if it was just the inductive load, the utility company would have to supply this much power. And the power angle is now much larger. But if I add a capacitor in the circuit, now my power requirement drops. So power requirement is now only at this level. Let's take this QL out. So this is QL, which is 1 VAR. QC is 0.5 VAR. The actual power required is just here. That's how we get. Does that make sense? Right? So the process of applying a capacitor to reduce the power requirement locally is known as power factor correction. Power factor is defined as the cosine of the power angle, cos of theta, right? So cosine of the power angle. The larger the angle, the smaller the power factor. And power factor is expressed as a percentage. So ideally, the biggest, the highest, largest value of the power factor would be 100%, meaning I do not require any reactive power at all, right? If I do not require any power factor, do not require any reactive power, then the angle is 0, cos of 0 is 1 or 100%. As the angle gets larger, the power factor increases. So 0.9, 0.8, 0.7, so 80%, 70%, 60%, so on and so forth. In real life, if a customer does not have a certain power factor, then the utility company will not supply electrical power. The utility company would tell the customer that, hey, you need to get your power factor up before we can flip on the switches. So they won't even supply electrical power. So industrial customers have to pay for the real power, and they also have to pay for the reactive power, even though they don't use actual reactive power. Because some of the reactive power is supplied, and thereafter there is local capacitors that actually supply the reactive power requirement for the inductive load. Now, power systems analysis is a whole different area of specialization. So this is not even like skimming the surface. We're basically out of the pool. We're just like looking at the surface. We're not even like snorkeling. Sorry, what? Yeah, maybe in a puddle, yeah. But hope all of this makes sense. Like, this is a very bare bones, simple explanation of inductive reactive power and capacitive reactive power. I will show you the use of that last equation. Half VI asterisk. These are both phasors, right? V and I are both phasors here. So voltage V had a magnitude of 10, phase angle of minus 90. Current was 0.1414 with a phase angle of minus 135. Complex conjugate would simply be 135. You solve this and you obtain, let's see, what do we obtain? 70 point, not 70, 0.707. 0.707 with a phase angle of 45. Exact same answer, magnitude of 0.707 with phase angle of 45. You transform this into rectangular coordinates and you obtain 0.5 plus j 0.5. It's the exact same answer again, no difference. So this is kind of like a one-step answer, right? Half VI asterisk. Previously, you had to solve for P, you also had to solve for Q. Now, if you want to plot the power triangle from here, then you equate it with P plus JQ. So this gives you P, this gives you Q. Power factor, again, in the video, if you have not checked out the video, I would strongly urge you to do so. You also state power factor as lagging or leading. Simply put, inductive power factor is lagging. Capacitive power factor is leading. Because for an inductor, the current always lags the voltage. For a capacitor, the current always leads the voltage. So again, it's there in the video, but suffice to say, for inductive load, power factor is lagging, and for a capacitive load, it's always leading. All right, questions? Any questions at all? Yes. Here? No, it's So the current that we found earlier was 0.1414 with an angle of minus 135. Complex conjugate simply means it's now plus 135. No, that was, so current was 1414. Where's current? Right here, minus 135. Yeah. Any other questions? I have a few important announcements, so don't be in a rush yet. Any questions? Okay, so homework for AC power is it due on Sunday? Okay, if it's not due on Sunday, I will make it due on Sunday. But some students are saying it's due on Sunday, so it's great. Monday is, well, it's Thanksgiving week, so you're basically no classes, Thanksgiving break, but we will still have a quiz. The quiz will be available from 9 a.m. to 9 p.m. You have 12 hours to work on it. Well, you don't have 12 hours to work on it. You have 12 hours to get it done. Once you open it, you'll have about 30 or 40 minutes. I haven't decided what evil problem I want to have on there. So I'll take some time and do so. But it's going to be something similar to this. AC power analysis. It's a guaranteed problem in the final exam. It's a combination problem. You solve first for the currents and voltages, then you solve for the power. Okay. So yeah, and that will be the last quiz for the quarter. So once you come back from break, no more quizzes. Last quiz of the quarter, which is next week. Also, I have another example right here. I will solve this and I will have detailed steps. I will solve this step by step. So it's a self-contained solution that I will post on Canvas. No more video. My voice and my coughing attack, I won't have. Yeah, video is probably not a good idea for me right now. And so I'm going to solve this and have a document. I'll post it on Canvas. Definitely look at it. If you have any questions, you let me know. Final exam. Here's the part that you'd be interested in. Final exam is going to be on Saturday, December 4th. Hold on. That's just half the information. So it's a common final. In case you haven't checked it out, final exam date has been posted on Canvas since the beginning of the quarter. Okay, it's right there on the front page. It's been there since the beginning of the quarter. So let's see. This is right there, final exam. So according to the university's schedule, your final exam, again, this is not something that I have decided, it's the university's final exam schedule, is on Monday, December 6th from 10:10 to 1 p.m. right here in this classroom. I also have a common final, the Saturday preceding finals week. So December 4th from 1 to 4. You have the option of taking the common final, get it out of the way, so then you can concentrate on your major classes during the finals week. You don't have to give me an explanation on which one you choose. Okay, you just have to let me know whether you're taking it Saturday or whether you want to take it at its regular scheduled time on Monday. All right. So taking the common final is not mandatory. I'm not compelling anyone to take the common final, but I would need to know who wants to show up. All right. Then, if you have multiple exams on the same day, you also have the option of taking the final with my other sections. Those other sections have exams on Wednesday and Friday. Okay, so instead of Monday, it's Wednesday or Friday. For that, you do need to explain your reasons. Okay, so taking the common final or not, you don't have to explain. But if you don't want to take it on Monday, then you do have to explain to me in an email. Again, the exams, Monday, Wednesday, Friday exams are in this classroom. As you can see, there's a limitation on the number of seats. So again, if requests and approvals exceed the number of seats, I cannot basically approve more than that. So I will have all of this information in an email about the quiz. Quiz email will be separate. The final exam email will be separate. Expect them to come out sometime later today. Yes. No, because we still have one more topic to actually get, like two more topics to get through. So last day of class, I typically do not, I just do like a short review, like 15-20 minutes, and then the rest of the time is free for students to study or relax, take a nap, whatever they want to do. So if students want to take the common finals, some of the students in the past, they take the class time to actually, study and prepare for the final on Saturday. So we only have like two more lecture classes, like Monday and Wednesday. If you're traveling on Monday, if you have something going on, you send me an email as soon as possible. I will make alternative arrangements. Right? Yes.
Is the common final gonna be easier?
That's a good question. So, and I forgot that important point to say. Yeah. So all the finals will be different, but they're going to be on the same level. They're not, if you take it earlier, it's not going to be easier. If you take it later, it's not going to be tougher. They're going to be pretty much on the same level. They are not going to be, it's not easier or tougher or anything like that. Yeah. Yep. Fair question. Yeah. Yes. This Saturday after last day of class. What do you mean? Oh yeah, I make all of the finals. Yeah, common final is not the department. It's just me. Yeah. Yeah. All right. Have a good break, and I'll see you all in 2 weeks. Well, not 2 weeks. Sorry, week from this Monday.